We think so if we're talking about the spanning tree, when we have a graph G and we have some subgraph T, so we can denote it like this, some subgraph T, that is a tree and that spans all the vertices of the original G. That's a spanning tree. So we can give an example. Let's say we have like a graph that contains this many edges, and obviously we see that if we remove some edges we will still keep all the vertices, because if you remove something called the leaf, for example, that's a vertex that only has one edge connecting it, by which it's connected to the rest of the graph, then that vertex would be deleted if that edge to which it's attached would be removed. But here we see we can remove edges without removing some vertices. So again, it's a tree subgraph that has all the vertices. So there's this condition. I mean, T is 3, as I said, and also the vertex set of T stays the same as the original vertex set of G. So in case this is G, let's for this example find the spanning tree. So let's draw all the vertices and think of which of these edges are necessary for all the vertices to stay. Well, what we can do is just take, let's say, these 3. We take these 3 and we still keep all the 4 vertices, and we removed both this edge and this edge. So also this introduces the notion of the idea that it's minimal. So as we see, again, if you look at different variants of this case, you cannot find a subgraph that's a tree that has a lower amount of edges. So we minimized the number of edges but kept all the vertices. So once again, this is a subgraph T, and it retains all the vertices, but we can remove edges as long as that graph is not a tree. So and now it's a tree. Now what we got, this T here, if this is T, we got this subgraph that is a tree. So it's called a spanning tree. As long as we span the original graph's vertices, we reduce the edges until it becomes a tree but retains all the vertices.